Chapter 4, extra practice here. You are given a table, and so anytime you see the table like so, you're thinking a discrete probability distribution. We're thinking discrete and not continuous because remember with continuous, there's an infinite number of possible values. A continuous distribution cannot have a table. And so we think it's discrete. Now, could it be binomial? Maybe, maybe not. But in this case, if it's binomial, it's kind of irrelevant because we can do all of the things with just knowing it's discrete that we can do with the binomial formulas. The benefit to the binomial formulas, of course, is that it makes life a little bit easier. We can shortcut, we can find those f of x if they weren't given to us, but they're given to us. So we don't need to plug in to find the probabilities, which is again one of the key benefits to having the information that a problem is binomial. You've already got the f of x's, so you don't need that. So we've got everything we need here in this discrete table. X represents the number of bullseyes thrown in 3 throws. The first question asks you to find the expected number of bullseyes using the correct symbol. So first off, recall expected number, mean, average are all synonymous terms. And then using the correct symbol, what I'm trying to make sure that we understand is that you have to differentiate between X bar and mu. Is this a sample mean or is this a population mean? Remember that a sample mean is a mean of a sample. It's a mean of we did a sample. A sample's a subset. We took some observations, right? A sample mean would be the idea that I went out and I threw darts a handful of times and I found metrics on that, as opposed to a population mean as I'm trying to find the mean of all the possible throws that could be made. And notice that in a discrete probability distribution, there's a key word there, and that's probability. The idea here is that probability, which we defined in chapter 3, is a long-term measure of success. It's implying the all. It's implying the what if I know the true probability, the true value of how many bullseyes I would get in this scenario, as opposed to, again, what if I had said, I went out and I did this 20 times and here were the results. That would be a sample mean. But when we talk about a discrete probability distribution, we're always talking population metrics. And so the correct symbol would be mu. We plug into the formula that you are given. And then from there, it's just simple math. Take every x, multiply it by the f of x, and then sum those up like so, and you would get 2.7. Next, write the probability statement and find the probability that Viper gets at least 1 bullseye in 3 throws. So again, anytime you see write the probability statement, even if it says find the probability without that, write the probability statement. Let's see if we can, of course, get that piece first, and then we have to say, how do I rewrite that? Okay, the way that we're working these probability questions here in chapter 4 and in our next chapter as well is going to be write out the probability statement, then how can I rewrite that into something else that gets me to the answer that I'm looking for? And so in this case, I could rewrite that as the probability that x equals 1 plus the probability x equals 2 plus the probability that x equals 3. You could add up those 3 numbers and that would absolutely give you the correct answer. Alternatively, you can write this as a complement and write 1 minus the probability that x is less than 0. Remember with complements, x is less than 1. Remember with complements, we rewrite that as 1 minus the probability and we flip the inequality sign and we change the or equal to. And then of course the probability that x is less than 1, there's only one value that is less than 1, that is 0, and so it's 1 minus the probability x equals 0. Be careful when you write these. I see a lot of students, and what they'll do is they'll just say 1 minus 0, and what they mean is the probability x equals 0. That's not the same thing. This is its own quantity, this probability. This probability can be replaced with a number as opposed to saying 1 minus 0. And I get what you're trying to indicate, but you need to be careful about what you're communicating. Probability x equals 0, that is f of 0. That's this value in the table, so you simply plug that in, and then you've got your answer. And now the last question here, is this a probability distribution? As we talked about earlier, it's not necessarily relevant to the work that we're doing in the problem because we were given the table so we can do everything there, but we just want to think through, is this binomial? As mentioned before, anytime we have a binomial setup or a question, if it's binomial, we have to ask ourselves, does it meet those 4 criteria? Go through them one by one. In this case, you would say yes. While it is not while P is not given, P represents the probability of getting a bullseye in any one throw, right? We don't know what that is, but P is always just the probability of success in one trial. And we said we could find that. It would not change, right, from one throw to the next throw. It's your skill level is kind of your skill level. You're not going to magically get better after one throw. There are only the two options, right? You either get the bullseye or you don't. There are a fixed number of trials. There are only 3. And kind of as we talked about, the probability of success doesn't change. The throws are independent. And again, as mentioned before, those are correlated concepts. It is possible to not have one or the other, but a lot of times they do go hand in hand. In this case, they do. You're not going to be more or less likely to be successful on your next attempt just because of what happened on the previous one. The probability of success is remaining constant. So we would say that all 4 criteria are met. And so, yes, this is a binomial setup. And then for our last example, 60 people are stopped on the street and asked for the race. For ease of calculations, assume that half of the US population is white. This problem can be worked without the use of a calculator. So I've given you some really simple math to compute here. So kind of just a prep for an in-person exam where there is no need for a calculator as opposed to work that is on MyOpenMath. It is usually more complicated. Using the correct symbol, find the probability that one randomly person chosen is white. That should be fairly simple, given to you in the problem. P is 0.5. I want to make, of course, the distinction as we've talked about the difference between P is the probability of success in one trial, whereas when we ask about the probability of success over a series of trials, we don't have a symbol for that. We write out a probability statement for that. So make sure we keep those separate. Using the correct symbol, find the mean of this distribution. Again, mean, average, expected value. And the same thing we discussed on the last problem, that this is a mu, not an x bar. And again, it's pretty straightforward. You are given the formula n times p. 60 times 0.5 is 30. And again, we can attach the units onto that. That would be people. Using the correct symbol, find the variance. Remember, on the formula that you're given, variance is n times p times q, where q is 1 minus p. If you're asked for the standard deviation, you will need to square root that. In this case, we are not asked for the standard deviation. So we just get to plug in to the formula 60 times 0.5 times 1 minus 0.5, which is also 0.5. That is 15. And here our units are squared, right? Variance is always measured in units squared. Standard deviation is always measured in regular units. Write out the probability statement. Define the probability that exactly 20 people in the group are white. And again, this is, as we mentioned earlier, the difference between having the symbol of P as probability of success in one trial. This is the probability of 20 successes in the 60 trials. This is just set up the problem. This is one that you would not be expected to calculate without help of Excel or a calculator. And so I'm not asking to here. Just make sure you plug the numbers into the right spot. Be careful here. This isn't, again, meant to trick you. It is just meant to see, are you paying attention to detail? Are you paying attention to where things go? As long as you are being careful there, then this should be no problem. 60 minus 20 is 40. That's how I got that number right there. And the last question, what form of bias is likely present in the sample? This would be sampling bias. This says 50 people. That should read 60. But that's completely irrelevant. We stopped a bunch of people on the street, but depending on where we are, it is almost assuredly not the same racial makeup of the country as a whole. So again, this is where we just want to stop and think through. Anytime we ask about biases, think through, is the sample representative? Do we have a good sample? If not, that would be sampling bias. Are the responses likely to be accurate? That would be response bias. Or did we ask for a lot of people to respond, not a lot did? That would be non-response bias. In this case, you might think about a response bias, but I don't necessarily think that when you're stopping someone on the street, you can see them, you ask them for their race. There's probably not a lot of response bias there. But if you talked about that, as long as you're giving good justifications, it's not really a problem. Just don't go hunting for something that's not there. But if you give a good justification for that, then response bias could be appropriate there. But the biggest thing here is sampling bias. If you just think through what we talked about, as we said, assume that half of the US population is white, but there's only a handful of places in the country where that specifically is true. There's a lot of places where it's a lot higher than that. There's a lot of places where it's a lot lower than that. So because we just stop people on the street in one location, there's a decent chance at least that we weren't in one of those places. And so we don't have a good sample here. The way to correctly work this sample would be to get people from all across the country and have a good representative sample of people across the country, which we did not do in this problem.